Good day, ladies and gentlemen, and let us continue our search, our discovery, our quest to understand chemistry. And today we want to go back and take a look at heating curves again and do another couple examples of heating curves. So let us review a little bit. We're talking about heating curves, right? And a heating curve shows what? Shows temperature change versus heat added, and we look what happens to the substance as heat is added. And let's say we start down here. Usually what happens, we'll start with a solid phase. And then once I reach a certain point, this is going to be what? This is going to be the melting point, freezing point. Then I go through a stage where it's flat. And let's talk about this for a second here. So this is solid, right? And what happens as heat is added? Well, as heat is added, all that heat goes to increasing temperature, meaning what? All that heat goes to increasing the average kinetic energy of the particles until I reach this point. And then what happens? As more heat is added, my kinetic energy doesn't change. Why is that? Because I'm converting my solid into what? Into a liquid. Okay? So that means all the heat between these 2 points goes into converting from a solid to a liquid, and we call that fusion, right? And so that's the heat of fusion. Oh, nice straight line there, isn't it? And then as more heat is added, once all of my solid is a liquid, right here it becomes a liquid. Once it's all a liquid and I continue to add heat, then my kinetic energy increases again, meaning my temperature increases until I reach this point. And at this point, I start transforming from a liquid, there's a liquid right at that point, to a gas, right? And what do we call that point at which a liquid starts becoming a gas? We call that the boiling point. And what is the process called? We call this vaporization. Vaporization, right? And once again, like fusion, it is a phase change. And all the heat that goes in here is to do what? To overcome the intermolecular forces and convert all the particles from a liquid to a gas. And then once all the particles are a gas and I continue to add heat, what happens? The kinetic energy of that gas increases again, and it goes on until I stop adding heat, right? Cool. And we can go in this direction, and that we call that fusion. But what if I go in the other direction? What if I'm coming down this, I'm removing heat, and I go from a liquid to a solid? What do we call that? We call that freezing, right? And what do I call the opposite if I am removing heat from a gas and I go from a gas and I convert from a gas to a liquid? What do we call that? We call that condensation, right? And these are our phase changes. And we can look at what's the total amount of heat that I'd have to add. Well, to determine the total amount of heat, we really have to do 5 calculations, right? First, I have to deal with the heat of the solid. And the heat of the solid is equal to Q solid, which is equal to M solid, C sub P solid, delta T solid. And remember that delta T is only from right here to right here, because anywhere above here it's no longer a solid, it's a gas. Then I have to worry about the Q that goes into fusion, the heat of fusion, right? So how do I get the Q of fusion? Well, that's going to be usually my mass times delta H fusion. Now, we have to be careful because sometimes my delta H fusion, it's not, usually for us, it's going to be in kilojoules per gram. Sometimes, though, it might be in kilojoules per mole. And if it's in kilojoules per mole, this number has to be moles, not mass. So keep an eye out for that. Let's erase some of this beautiful work of mine and go deeper into this, right? Now, how do I get my Q of liquid? Well, Q of liquid is equal to my mass of my liquid, C sub P of my liquid, times delta T of my liquid. And what's the delta T of my liquid? Delta T of liquid runs from here to here, yoink, from my melting point to my boiling point. And then I have to deal with this, and what is this? This is Q vaporization. That's all the heat required to transform all of my liquid into a vapor, and that's going to be M usually mass. We have to watch out. Sometimes moles, like I said, times delta H vapor, right? And this is my latent heat of vaporization. That's usually given to us. And then finally, we have Q of my gas, which is equal to M gas, C sub P gas, delta T gas. There we go. And then I add all of these pups together, and that would give me my total Q. And we just have to make sure that the units are constant, because sometimes out of here I'll get a kilojoule, and usually out of here I'll get a joule. So you have to make sure you convert everything either to joules or kilojoules. Got it? And that is our beautiful heating curve. Let's take a look at a question. Consider 727 grams of water. Okay, that's my mass. And it starts at 35 degrees Celsius. How much heat is required to transform this to steam? Steam, that's a gas, at 115. Okay, good. So let's take, I always like to draw my picture. So you go zoink and zoink and zoink and zoink and zoink, right? And this number for water is what? That place is 0, and this number for water is what? 100. Okay, here's my temp, and here's my heat. Good. Now, let's see what is given to us. It says I start at 35 degrees. Okay, where's 35 degrees? Is that here? Is that here? Is that 35 degrees? Is that 35 degrees? Is that 35 degrees? No, these are all zeros, so where's 35 degrees? Well, it's got to be between 0 and 100, so maybe right here is where we start, 35 degrees. Aha! So what's different about this? What's different about this is we're starting here, and we're going to go like this. Good. So do I have to worry about the heat of the ice? No. Do I have to worry about heat of fusion? No. Where do I start my heat concern? Right here with liquid. So I want to find heat of my liquid. I want to find heat of my vaporization, and I want to find heat of my gas. So we've made this question actually easier. So let's find Q liquid. Q liquid we said is M C sub P liquid delta T. What's my delta T? I'm going to go from, remember delta T is T final. What's the final temp here of my liquid? 100. Minus what's my initial temp? 35. Is that 35 or 35.0? 35.0. Okay. Then we'll drop another sig fig in my 100. Got it. Cool. And so what is that? The difference here is 65.0 degrees Celsius is my delta T. All right, here we go. What's my mass? My mass was 727. 727 grams. What is my C sub P? C sub P of what? C sub P of liquid. 4.18. 4.18 joules per gram Kelvin times my delta T. 65.0 degrees Celsius. And remember, a delta T in Celsius equals a delta T Kelvin. So these guys will indeed cancel as long as we're talking about change in temperatures, right? Cool. Okay. 727 times 4.18 times 65. And I get a beautiful number. Let's hope this is right. 197525 joules. Let's add that up. Let's try that again. 727 times 4.18 times 65. 197525. Good. How many sig figs? Looks like I get 3 out of this. So these guys are carried over. How about my Q vaporization? Well, that's going to be my mass, I think. Let's take a look at my units here. Vaporization is kilojoules per gram. Good. So that means I need mass. So that means I'm going to go with my 727 grams times my 2.26 kilojoules per gram. And let's go ahead and convert this to joules times 1,000 joules per 1 kilojoule. Got it? Okay, let's run this bad boy. 727 times 2.26 times 1,000, and I get a 1643020. Let's make sure my numbers are right. 727 times 2.26 times 1,000. And I get 1643020. Good. How many sig figs? 3. Okay, so I can only have 3 sig figs. And that is in now joules. And then the last, We're going for Q of my gas, and that's going to be my 727 grams times C sub P of my gas. What's C sub P of my gas? Where's C sub P? Right here. C sub P of gas is 1.84. 1.84 joules per gram Kelvin. And what's my delta T? Where did we stop? 115. So that number here is 115. What is that? I go do. That's 100. So 115 minus 100. 115 minus 100. And that looks like 15. So I get 15 degrees Celsius. That's my delta T. And it looks like that's I only have two sig figs there. 727 times 1.84 times 15. Do I get it? Sure do. 20065 joules. Let's check that again. 727 times 1.84 times 15. Good. So I add these guys up. Plus 1643020 plus 197525. Okay, so I got 1860610. Let's check that again to make sure I did this right. Lots of numbers. This is not hard, but it can be tedious, and we can make mistakes easily. 197525, got it, plus 1643020 plus 20065, and I get 186. Okay, good. Now how many sig figs? This is significant to the thousands. This is significant to the what? 10,000s. 1, 10, hundreds, thousands, 10,000s. So it looks like it can only be significant to the 10,000s. So this is ones, tens, hundred, or ones, tens, hundred, thousands, 10,000s. Is that right? 1, 10, hundred, thousand, 10,000. So it's only significant to that. I have to round those, so it's going to be 1860000 joules. And if you want to get rid of the joules, we can move this and turn it to kilojoules. Got it? All right. You guys give this one a shot and bring me back when you're ready. Well, what do we have here? I start off with ice at minus 35. And you want to know how much heat is required to make it water at 77. So if I draw my picture, where do I start? I'm going to start here. I'm going to go here. I'm going to go here. This starting position is what? Minus 35. This is going to be 0, right? Because it's the freezing point. And then I'm going to go up to, do I go up to 100? No, I only go up to 77. Yahoo! So I stop at 77. So does this vaporize? The answer is no. It does not vaporize. So we only have 3 steps to our calculation. I have Q solid. I have Q fusion. And I have Q liquid. Those are the only 3 I have to deal with. Good. So Q solid is going to be, what is my mass? 7125. Ooh, big number. 7125 grams. C sub P of ice. We should almost have that memorized by now. What is it? 2.09 joules per gram Kelvin. And what's my delta T? My final temperature is 0. My initial temperature is minus 35. How many sig figs did I give it? 35. I gave it 3. Okay. And so what do we have? 7125 times 2.09 times 35. Yoink! That looks to me like a 521193 joules. Let's check that again. 7125 times 2.09 times 35. 521193. Yes. So what is my Q of fusion? My Q of fusion is going to be what? 7125 grams times, where is fusion? Right here, 0.334. 0.334 kilojoules per gram times what? 1,000 joules per 1 kilojoule. Got it? Yahoo! And what does that equal? 7125 times 0.334 times 1,000. And I get 2379750 joules. Let's make sure that's right. 7125 times 0.334 times 1,000. 2379750. Okay, cool. And then how many sig figs? 4, 3, 3. I can get 3 sig figs, so those are not significant. I can get 4, 3. I can only have 3 sig figs here, so those are not significant. And then Q liquid, 7125 grams times 4.18 joules per gram Kelvin times what? 77.0. Yep, that's my final temp. 77.0 minus 0.0. And so what do I get out of that? I get 77.0 is my delta T. Cool, here we go. So I get 7125 times 4.18 times 77, and woohoo, magic. 2293252. 2293252. Okay, let's check that number. That would be indeed what? Joules. 7125 times 4.18 times 77. 2293252. Okay, good. So when we add these all together, what do we get? I get 521193 plus 2379750 plus 2293252 equals. My total then is a 5194195. 3 sig figs here. So this is tens, hundred thousands. Nope, how about ones, tens, hundreds, thousands. So this is significant to the 10,000s. 1, 10, hundred, thousands. This is significant to the 10,000. Is that right? 1, 2, 3, 4, 1, 2, 3, 4. This is significant 10, hundred, ones, tens, hundred. This is significant to thousands. So I'm only significant to the 10,000s, right? So that means 1, 10, hundred, thousands. So those guys are not significant, so I need to round that. So this becomes 519,000 joules. Let's add that up one last time to make sure we're right. So it looks like it should be 190 plus 2379750 plus 2293252. Good, I get the same answer. There we go. If you guys get an answer like this, then your answer is like mine, and I hope we are correct. Well, that would be it for the heating curves. Like I say, this is not that difficult, but you must be careful with your units and your addition. Make sure you don't make any stupid mistakes. All right, that would be it for today, and that's all for heat. See you next time, and we will talk about kinetics.